Okay, chapter 12 is angle measurement. Okay, so all length and angle standards, they are arbitrary human inventions. Circle is one standard that exists in the nature. For example, the path of an electron around the nucleus of its atom and the circumference of a planet. So these are all naturally existing circles. So the circle is a universal standard, and the division of a circle started the angle measurement. Squares looks like this, just a tool, and they are the most basic angle measurement instruments. The trigonometry concepts, they date back all the way to ancient Greek and Egyptian engineers, and they used trigonometry to measure objects they couldn't be able to measure directly. These objects are the angles, and trigonometry is now in every phase of the technology. So when you think of a circle, it's same as the line. Okay, it's consisting of points in a plane and all equally distant from a center point. So you have a center point and you have points in a plane, and they're all equally distant from a center point, and we call that kind of shape a circle. So it is different from all other curves because it is the same at all points. Roundness is just a characteristic of all circles. The radian is the angle subtended by an arc of circle, so that is equal to the radius of your circle. So we use this measurement to deal with angular displacement like gear rotation. So if you want to review what radian is, make sure you study physics 1 and 2. So this chapter focuses on the measurement of angle based on the circle. So when you take a look at it, this chunk, and we call the measurement of this little pointed section is the angle. And the principle is a right triangle trigonometry, because when you dissect a circle, you can get many different kinds of triangles, including the right triangles. So we can definitely use the right triangle trigonometry. Angles, they deal with directions, not spaces, because the angle is a relationship between two lines. So you can see the lines crossing the center are dissecting the circle, forming angles. Okay. So we can extend the lines until they intersect. So the intersection is called little one right there, vertex, and the lines right here and here are the sides. So when you take a look at angle AOB, you can see the O is at the vertex, and the sides are OB and OA of the angle AOB. Okay, and it refers to the directions of the sides, not to the space in between them. So we're thinking about these two lines and their direction every time we measure the angle in between them. Okay, so when we define an angle, we use 3 letters to designate an angle. For example, angle AOB. You're going to read it angle AOB for this little symbol. So the symbol angle is designated to an angle. And do not confuse with the less than symbol, which is like this. Okay, so this is more of a linear. This is kind of slanted, so a bit different. So for right angle, we use right angle. See, that's totally 90 degrees to each other. These two hands are. So for example, right angle AOB. That's not right angle, that's just a simple angle AOB. So right angle AOB reads the right angle AOB, which has actually 90 degree measurement. So a right angle is 1/4 of a circle, because you have 4, okay, 90 degrees in a circle in total. So, or 1 quadrant. Since there are 4, we call 90 degree of a circle a quadrant. So if an angle measurement is less than 90 degree, it is an acute angle. if it measures more than 90 degrees, it is obtuse angle. So 45 is less than 90, so we call this little angle acute. And from here to here is 315, that's more than 90, so we call that obtuse. So here the same thing, that's 225, and this one is 135. Both of them are more than 90, so they both are obtuse angle. And we can see here the right angle is 90 degree and less than 90. Okay, we're going to call this little angle acute angle. More than 90, the bigger angle, we call it obtuse angle. So an angle can be measured in either direction. We could measure angle AOB from one direction as 315 degree, or from the opposite direction as 45 degree. Okay. So again, another angle AOB, so 1, 2 here, AOB, and we have 225 angle AOB, and we have 135 angle AOB. So looking up from this direction and looking the vertex from the other direction, okay? Okay, so to minimize ambiguity, we use the term supplementary and complementary, but sometimes students become more confused when we apply these two terms, okay, and they want to just stick to the old way of saying on the previous slide. So we always have two angles. One is the acute, less than 90, and an obtuse is more than 90 on a half circle. So they usually total 180 degrees. Because a half circle has two quadrants, each quadrant is 90, so therefore two quadrants is going to give you 180 degrees. So the acute is called an angle and the obtuse is called a supplementary angle. Okay? So just make sure you understand the supplementary. We're talking about the acute and obtuse on 180 degree plane. So supplementary angles total 180 degrees. Two angles that total 90 degrees, they're complementary to each other, so angles are expressed in terms of rotation in the same direction. So either clockwise, going this way, or anti-clockwise, going that way. So for example, 60 degree, okay, counterclockwise, and then 300 degree clockwise. So here we're going counterclockwise, backwards of your clock, and then 300 degree clockwise on the clock, okay? Here the same thing. Complementary is at angle B, and then O, and then C. Angle AOB is just an angle, okay? And they're within the 90 degree, meaning when you add these two angles, they should give you 90 degree. So complementary angles, they total each other 90 degree. Supplementary angles, they total each other 180 degree, okay? So again, you pay attention. So angle is your AOB, your supplement is BOC, this big angle, okay? Okay, this is just a middle school review. So the relationship, you have two lines here, they are parallel to each other, line A and line B. And the angle is shown, okay, in the line. So you have 1, 2, 3, 4, and 1, 2, 3, 4 angles. So this is just a review for your middle school. Pythagorean Theorem is nothing but it states that the sum of the squares of the sides is equal to the sum of the hypotenuse. Okay, so when you take a look at here, you're going to see in this case is actually that's a square. Okay, I don't know what. So a square is equal to c square plus b square. So we usually give a little b, okay, for the side for the angle B, little c for the side for the angle C, and little a for the side for the angle A. So that's just your Pythagorean theorem review. And the right angle was probably first used for actually surveying in ancient time. So when you take a look at these four angles, okay, you're going to see if these two lines are parallel, Okay, your x is equal to x1, 2, and then 3, and your y is going to equal to y1, and then y2, and then y3. So if you cannot see it, it's right there, okay? So the x is equal to x1, okay? And this is equal to that is equal to this, okay? That's usually, you can take it just going across like that, okay? Your y, the same thing, going this way, okay? Imagine there's a circle there, so that's your vertex. So these angles they're the same, okay? I want you to try to imagine, and when you look at it, you should be able to see this geometry in your head. So when you see the two lines intersecting across a point, you can be able to imagine a circle around it. Okay, so in that way, your vertices, the angles of the vertices are the same. So that's how we understand the geometry of most of the lines. Okay. You should be able to dissect the geometry in your head by just looking at them, so try to practice that. So the sum of all angles for a triangle is again equal to 180 degrees. Doesn't matter right angle, okay, or a triangle of any shapes. So you add the angle ABC, angle ABC here inside of each triangle, they're going to give you a total of 180 degrees. Yeah, this is just another review from your middle school math. So if one angle of a triangle is the same as the angle of another triangle, so here in this case, your angle A is equal to the angle letter C right there. So at that time, the sides of these angles are proportional. So for example, here little angle A and this is little angle C, they are equal to each other. Okay. So then the side M is proportional to the side P, the side O to R, and the side N to G. Okay, so another review is your trigonometric functions, and that's also from your middle school and high school. So these functions are very important because they let us designate in relationship to the ratios of the sides of triangles. So they're useful tools of measurement. So when you take a look at this right triangle, the hypotenuse is the longest side. The side, okay, opposite, you can also call the opposite side or adjacent side. It's the same thing. Okay, I don't know why this author is saying reverse. Okay, so anyways, when you take a look at this, and here is your given angle. If the side is opposite to the given angle, we call the opposite side or side opposite. If the side is adjacent to the given angle, then we call that side adjacent or adjacent side, the same thing. And you can get sine, okay, of this angle, given angle. All you have to do is divide this opposite side by the hypotenuse. If you want cosine, divide the adjacent side by hypotenuse. And then if you want tangent, you're gonna divide the opposite side by the adjacent side. If you want cotangent, you're gonna divide the adjacent side by the opposite side. Okay, so make sure you get all of these ratios. Okay, so this figure 1212 is just giving you the equivalent instruments. And you can see the linear measurement and then your angular measurement. And this is just a type of your instrument if they're scaled or vernier or mechanical, standards of comparison, or optical. So in linear measurement, we have already studied the steel rule, combination square, vernier caliper, micrometer, gauge blocks, and comparators. Measuring microscope, we're going to come across it in optical chapter, okay? In angular measurement, we're going to study plane protractor, protractor heads of combination set, vernier protractor, index heads, angle blocks, and sign devices with comparators, and auto collimators, okay? These are just for the optical instruments. they measure angles, and these instruments, they measure linear measurements. Okay, square is just an instrument to measure the angle. So when we bisect a circle, we get 280-degree angles. And the perpendicularity is the measurement of an angle, a right 190-degree angle. The squares are hardened steel, okay, right angles. So here you can see it's totally 90 degree to each other. This instrument is built, and they're available in wide range of sizes and shapes. So you can see many different squares. So the combination square is the right angle measurement instrument, and we use the inside, okay, or outside of them for comparison measurements for observations. So it depends on the shape of the objects that you're measuring their angles. So here when you look at the functional feature of your precision square, you're going to see the knife edge, and then the blade, and you have a little clearance groove, and then the beam. They're a little bit different because do not confuse with this side and then that side. And definitely the square got to be at 90 degrees, and this is your height. And highest accuracy, this is how far we can go, 100,000, okay, in precision and accuracy. This is just your tolerance zone that your square can deviate. This is a very exaggerated picture. The tolerance is of course very, very minute. Squares are accurate when used with a narrow edge of their blades along a diameter of round parts or perpendicular to the surface of the flat parts. Okay. So here in this picture you can see highly precise square, and we call that master square because it provides a stable base and a full reference edges. So the master square, most of the time we use it as a reference, or also the standard. Okay, the cylindrical square. So to calibrate a square, we compare it with a cylindrical square, and it looks like that. And it's a heavy ball and a steel cylinder, precisely ground and left, so that it is nearly a true cylinder. Again, we use them as standard or reference to calibrate squares, other squares. So here in this picture, you can see how to handle a 12-inch cylinder square, which requires care because it may slip, okay? So you got to lift it very carefully, and this is very wrong. And this is how you do it: roll, and then carefully raise one end into vertical position. So we usually store cylindrical square horizontally in a box, and then we're going to place vertically on a plate. So don't go this way because it's going to ruin the square, nick the surface, and smash your fingers. Go this way, roll it, okay, on the horizontal square, up over edge onto the plate, and then carefully raise one end into a vertical position. Degree of squareness. Okay, so squareness error. We usually measure it in seconds of arc. So we also measure the linear amount of outer squareness using micrometer, so that's mil, and we usually assume part is square to within 10 times the squareness tolerance of the instruments. Dial indicator and electronic comparator travel in the horizontal plane at some fixed distance above the reference plane. So you can say that every time we use the dial indicator, I have one in my lab, and I'm going to show you that. so it can definitely travel along the surface. Okay. And this is just our reference plane. So right now it's going along this axis because this little indicator, okay, head is going to travel on this surface. So when we compare the horizontal readings of an unknown square, this one, with a known one, we obtain a numerical measure of squareness. Okay, so we can only create a right angle only with a flat reference surface. So therefore we have to have something that is square. So squareness is actually created from the parallelism. So you can see the method here for attaining squareness from parallelism. So here you can see the parallel block because all four sides of this block are totally parallel to each other. Okay. So first we're going to cut the first cut and then we're going to grind it. So here you can see the first cut and cut the second one on this side and then grind it in this direction. So these are the grinding directions. And then we do the third cut and then grind in this direction. Okay, and the little dotted line is your original shape, and these are our cut block. And then we grind again. The more we grind, this parallel block eventually becomes a square. Okay, that's how we change the parallelism to squareness. So the reversible technique or reversible process is a method of doubling apparent error which halves the uncertainty in solving for the error. So even if we double the apparent error, what we're actually doing is we are taking down the uncertainty half. Okay, that way we solve for the errors. For example, if we have two blocks that are identical, we're talking about these blocks are so nearly alike that we can't find any measurable difference with available instrumentation. So if we measure the two blocks together and divide their combined length in half, each block will contain only half of the measure. So any flatness error in the reference surface will cause calibration errors, and it's vital that reference is accurate. So the resulting error in the measurement of the part is less than the error from the measurement of a single part. So when you take a look at it here, if you measure only just a single part, then that's your standard definitional part contains the total error. But when you do the two identical parts, okay, you have combined errors in the standard and measurement system here. So the new errors added by additional part. Okay, right here, the second one, which is identical to part one. So the definitional part contains half of your total error. Okay. So by using the two identical in measurement system, you will be downsizing your total error to half. Okay, so we use this method for square calibration, needing only a parallel, this one, with no master standard. So measuring the additional part definitely adds error. So first set up the parallel by clamping it to any stable support in a vertical position. Set the parallel by sighting along the square that is to be calibrated. Then place the square on the right, okay, of the parallel. So here is your square, and then here is your parallel. Okay, this is your beam of your square. This square is going to be calibrated, and this is the direction of your force. And then we're going to use gauges to calibrate between the square and the parallel. So here are little gauges right there. I'm going to put 2 by 2 of the same height. And these two steps provide a measure of double the squareness error. So the reversible process calibration, all you have to know is to be cautious to keep track of your plus and then your minus, plus and your minus signs for your errors. So the typical calculations are shown in figure 1223 right here. Okay. So when you take a look at it, the amount of error is half of the sum of your errors. That's because you have your right side parallel and then your left side parallel in your previous diagram. Okay, how we put the parallel next to the square on the left side and on the right side. So that's what we're talking about. And we have our bottom and then your top gauges. So they're using, that's a little bit different. One is 20 and the other one is 50 out of 1. And your out of squareness is the difference of that two. I'll circle on the same thing. So top and the bottom gauge is a little bit different, and the difference is this one 0.15 for this two on the left side, okay, of the parallel. So the amount of error, so what we do is we add the differences together, okay, and multiply with 1 by 2. So that's how you get the sum of your errors. The ideal situation is the gauges are the same, okay. Alright, the next one is your level. So everybody know a level. So one of the most useful instruments is your level because they are often used as parts of our instruments. So for precision measurement, we use precision level, clinometers, and theodolites. So we also use bench levels, mechanics levels in the shop, the one that you used to see. And these instruments have bubble right here, little one, in the fluid filled tube. So the bubble is affected by gravity. Okay, we always have gravity pulling to the core of the earth, so subjected to all objects and people all over the planet. So the tube is filled with spirit of wine, and we put it here, so therefore we sometimes call the level the spirit level. So if you take a look at your features, you're going to see your base of the level, and these are your nuts, your adjustment, and this is your plumb vial, and then this is your cross test vial, that's your bubble, and then this is your main vial or parallel vial, okay, and this side is your protective tube vial cover. So these are all the terms that you need to know for a level. So the least precise ones, they don't have the test vial, so it's just this one, and they also have shorter, okay, base. Spirit levels because they have spirits of wine inside of the tube where the bubble is. So the precision of the level depends on the curvature of the glass tube. So the longer the radius of curvature, the more precise the level will be. So when you take a look at this, so bent type, they have usually low precision. This one, when you take a look at it, it's kind of better than this shape, see? It's a ground type and they have higher precision. So the bubble and two references, that's the metrological features of a level. And they create geometric relationships between the gravity and the center curvature and the scale, okay, and the bubble position. So that's how the level works. So the level principle, you can see it right here. This is called your fiducial plane. So when you look at the bubble here, the graduated reference plane is here, and this is your radius of curvature of that, okay, where the bubble is standing, and here is your gravitational reference plane. And this is what we're talking about, the geometric relationships between the gravity, the center of curvature, and the scale and the bubble position, okay? That's how we determined the angles, especially the 90-degree and also the flat, okay, surfaces by using the level. So nature provides a reference from which a level expresses its value. In the center, it is seen that the graduated plane moves and the bubble remains totally stationary. This is just a table that's showing you the relationships of curvature to angle and then to rise. You don't really have to know it, just sort of take a look at it. So the precision of a level is usually expressed as seconds per division. Because angle we measure in degrees, and then the graduation that is smaller than the degree is your minutes. And the smallest graduations, smaller than the minutes, is your second. So we can measure the angle very, very precisely. But most of the time we're going with this degree units, which is the very first rough angle measurement. You always have a rise, because most of the angles are between two lines. So you have two little hands making an angle, so you always have a rise. So these are the different units that we can be able to measure the rise of that angle. So the actual rise per division is going to vary, among the instruments. Because instrument we have various design. And the actual rise per division will vary among the instruments because they have, again, various designs, and they're going to depend on width of the graduations. So since the bubble is inside of a fluid-filled tube, we can have thermal error. Thermal is nothing but your heat and your temperature error. So as with other measurements, temperature is going to affect levels by shrinking the bubble inside the tube. So the standard temperature is good at 20 degrees Celsius or 68 degrees Fahrenheit. So at warm temperatures above the standard, the liquid will definitely expand, reducing the length of the bubble. So the reading level, so you can see right here in this picture, so the centered position is marked by long graduations. So here you can see these are all short. And then right here, there are two long graduations. If you look at it quite carefully, and that's the center position. And the graduations at the end of the bubble, they're going to duplicate each other on both sides and corroborate the reading. So the left bubble in relation to the reader is negative, and the right bubble to the relation to the reader is positive. So A is showing you your center. B is a one division left, so when you look at the center right there, and then we have a one division going off to the left, and that's a 0.0005 inches, and that's your negative reading. And we have one division to the right, bubble is going, so you're reading your readings, and that's called the positive reading. And we're going off 3 divisions to the right, still your positive reading. There's no bubble, so that's completely out of range. So the bubble might be on this side or on this side. Adjustment, how are we going to adjust the level? They need to be adjusted all the time, so all levels with a sensitivity about 20 seconds or greater have an adjustment screw on it. So you're going to use that screw to adjust the level. So all you need is a flat surface when you do adjustment. Usually one direction across the surface is horizontal. One direction across is horizontal. This is trying to tell you to find a flat surface, and so that you can be able to adjust your level, because your level base needs a flat surface. These are just the steps to do your adjustment of your level. So first you're going to orient the level to the center bubble, and then you're going to clamp, straight edge along the level, and then reverse the level, divide the reading in half. Here is your screwdriver, that's your screw for adjustment. Correct the level by amount in step 4. That's just dividing the reading in half, So here we're adjusting that back, this little bubble back into the center. Then we're going to reorient the level to center bubble, okay, clump as before, and then reverse the level again and divide the remaining reading, and then correct as before. So what we're trying to do is putting this bubble back into the center, okay? So that's what we call adjustment, and you're going to repeat this step as needed. Even if we say like, oh, just get a flat surface or cross the horizontal line, even if we say that outside in the real world, theoretically we don't need a flat surface to adjust the level at all. So this is just showing you the reason the surface did not have to be level to adjust the level is figuratively shown right here, because you can still be able to manage to get this bubble back to the center without having a flat surface. Okay, even if in the outside world we say like a horizontal flat surface, if you have a horizontal line, even if it has an angle, you can still be able to adjust the bubble back to the center. Okay, that's what we're saying theoretically. So here in figure 1233, you're gonna see how to find the horizontal line to adjust the level. So select two lines across the surface that provide the same reading and bisect the angle they form. So the midpoint line approximates the level line needed to bring in the measurement. Okay, so even if it has a rise like that, if you could find a horizontal line, you can be able to adjust your level. Okay, so reversal technique, reliability. So this is just a table showing you, 1 to 5 for precision measurement, and that's for the reliability of your level. So we use reversible process for reliability when we use the level. So when precise measurements are made with a level, readings should be taken at both ends of your bubble, okay, negative and then the positive measurement, and then reverse the level and then repeat the readings. Reverse meaning like just flip it, okay. For precise measurement, take readings from both ends of the vial, reverse the level, repeat readings from both ends, average the 4 readings, repeat all steps for critical cases. So with the level sensitivity, every instrument has its own sensitivity. So the linear sensitivity is in level is inversely proportional to the length, okay, of the measurement base. So here that's the base of your level. So linear sensitivity, okay, is going to be inversely proportional to the length of the measurement, meaning like when the length is longer, your linear sensitivity is lower. When the length is shorter, then your linear sensitivity is higher. His level comparator is usually used for reliable measurement, and it does not need to be completely level. So this is just a 2 example showing you that the level comparator does not have to be completely level, meaning does not have to be completely flat, okay, to produce reliable results. So here is this kind of straight, okay, here it's kind of tilted, that's kind of tilted with a little angle right there, and here tilted on this side. Okay, so you can still be able to use the level comparator for getting reliable measurement without having a flat, or you can say straight or level, okay, line of measurement, okay. You can still do it even if you have one side is higher than the other. So you can see in 4 examples, each one of them is a little bit higher than the other side. But we can still get the reliable measurement by measuring in these kind of situations. So here's your metrological data for squares. This table just lists the these metrological data for your levels and your squares right there and tell you the reliability of that. So you can see all your instruments here and type measurement, the range, your precision, discrimination, sensitivity, your linearity, and this is just your tolerance, okay? And this is for your tolerance in manufacturing. So the four principles, disadvantages of levels are, first one is your general ignorance about their proper use and application. Most of the people just use whatever they want to do. With any kind of instrument, they usually do not follow what they're supposed to be following. They only do in the way they think it is. So that's kind of funny, but then that's the way they do it. So the length of, another one is the length of time required to settle down, and then their single sensitivity characteristic is also not very good in using levels, and they do not produce an output that can be used as loading for a measurement system at all, okay? So these are the disadvantages of levels. Protractor, so another instrument to measure angle. So, this is just a universal bevel, okay? Protractor. So it looks like that. It's kind of sophisticated. It's very different from our SAT protractor. So the protractor has a dial graduated degree. This one, okay, graduated in degrees units, so it's all grouped into 490 degrees because it's a circle. So the Vernier scale is again divided into here 24 spaces, okay? So we have 12 on each side of your 0 right there, so they're in minutes. So here the degrees are in degrees, okay? The Vernier is in minutes, so they go 60, 0, and then back to 60. So for minute reading, read the correct pair of lined up graduations, okay? So when you take a look at it, so this is your minute reading. So you have to read a pair, and you're going to see a pair that line up to the degree protractor graduation. And make sure you always read the vernier in the same direction from 0, that you read the dial and add the minutes to the dial degrees, okay? So here you can see the rule for reading vernier protractors. You're going to keep the same direction. Okay, you read the vernier in the same direction as your dial reader. So here, your dial reader, if you're reading from here to there, you're going to be reading from here to there. Okay, and then you're going to add that spaces to the degree. And when you add, you're trying to find the aligned, okay, look at this, so line up graduations between the minutes and the degree. So from here to here, okay, it's going to give you the minutes reading. Okay, so when reading from 90 degree, alright, so these are the positions that you can be able to see where the angle and its supplement are found. So remember, the angle in the supplement is going with 180 degree total. So when the protractor is set at 90 degree, we can again, okay, all 4 angles are red. So if you turn the blade counterclockwise, okay, so counterclockwise is going this way. Okay, like that. So the angle you read will represent only the angles formed from the blade to the base counterclockwise, which happens in 2 positions. So you can see the angle 80 degree, and then the supplement, okay, is going to be 180 minus the 80. The same thing, 90, and then the same thing, 100 is your supplement. Your angle is on this side, okay? And this is just a 90 degree, so you have a 90 degree 4 quadrants right there. So here you have 100, so your vertices, the other side is going to be 100, and this side is 80, and then 80, because you will have a total of 180, okay, in between the angle and the supplement. So here, the same thing, 80, this side is 100 for the supplement, okay? So you have 280 on that side and also on this side. When reading from 0, so there's a little danger of confusing the angle and its supplement. So when you take a look at this, same thing here, we're reading from 0, okay? You have your angle, and then you have your supplement. And you have to position the protractor accordingly to read the angle or the supplement angle. So here we're just trying to get the angle, okay, for 1, 2, 3, 4, 5, 6. So it's just hexagon, it's shape. So when you try to measure the angle of a hexagon, doesn't matter whether you measure here or here or here or on this side, you will definitely get 60 degrees. Okay, because the inside angle for hexagon is 60 degrees. Because when 60 degrees, 1, 2, 3, 4, 5, 6 of them added, you're going to get 360 degrees in total. So measuring acute angles. So even if a dial protractor, they rotate 360 degrees, we can't use the entire range of a protractor, okay, at all. And that's because a 15-degree angle, okay, when you set it here, is very little length of the blade, because the blade is pretty big. And the base and close angle, so reading turns out to be like 16 degrees in 15 minutes, okay, you're not getting 15 degrees. Even if you set the angle at 15 degrees, you can't get it because of the blade is interfering the measurement. So how do we solve that problem? So we attach, this attachment to form a reference edge. So the long edge becomes a right angle to the base, okay? So we're making a right angle to the base. So any angle we measure in this area is a complement of the angle so we want to measure. So we obtain the angle we're measuring by subtracting the attachment reading from 90 degrees. So here in this picture, we add a parallel extension of the base, okay, to the protractor to create an acute angle measurement device. So these are all the amplifications to solve the blade issue we have. So in this form of acute angle attachment, the readings are direct and they need to be converted. Precautions that we have to do using the universal bevel protractor. So this protractor does not measure the angle on a part, it measures the angle between its own parts. So the measurement must duplicate the angle, okay, before it can measure the angle. So here reading 55, then here reading 56. Then here the reading is 54 degrees. So therefore the instrument must duplicate the angle before it can measure the angle. And this is the best one. So when you take a look at it, here you have a rise there, and here you have a rise here, okay? The knots perfectly fit to each other like in A. So this picture shows you how to position the bevel protractor before measurement to make sure the blade is mated to the bevel surface. Okay, if the part features short like this on one side of the center, the measurement will contain a significant figure. So here we're rotating, okay, to the right. So if the rotation stops, okay, the blade is going to be mated to the bevel surface. Here you can continue to turn, okay, and the blade has already passed the mating position. So in this case, it's going to produce a significant error. So the true angle is measured only when the protractor is in a plane parallel to that of the angle. So you can see it right here in figure 1251. So when the protractor is resting on a part, it is constrained from translation in the z-axis, okay, but it's totally free to move in the x or y axis. So here, when you take a look at it, this is your z, and that's your x, and that's your y. They're free to move on these two axes, but then constrained right here on the z-axis, and that's the plane of the protractor, and this is the plane of the angle to be measured. So the plane of the angle here, okay, and the plane of the protractor here, and that's parallel to the plane of your angle. And the plane of the protractor, out of parallel, okay, rotation about your z-axis. It's a little bit difficult to see, so just take your time to be able to see these plane and then your 2D drawings. It's always difficult when you translate the 3D into 2. So the effect of rotation around the z-axis is shown in figure 1252, and we obtain a 38-degree reading when the instrument is parallel to the plane of your angle. So here we'll put in the instrument. Right here is 20, and right here it's trying to get 38, and here the blade is already made it, okay, and it's reading at 38. So here it's just trying to show you how important it is to position, okay, the instrument to where it is measuring.